All right, everyone. Well, here we'll be continuing our trek through homework 2 in our computational methods course. And in this part, we'll explain and code the secant and Newton methods for finding the root of a scalar 1D function. So we're kind of transitioning from this whole probability thing that we were doing to something a little bit um, different. So real quick, I'm going to import Jax. Uh, I'm going to import Jax because we'll need it in a second, right? And then import JNP. Okay. And so if you look at these methods, right, they're algorithms. So they're iterative methods to find a zero of a function, right? And so basically the secant method is you draw like a point, you draw a line between 2 points, and then you can see it here, right? Um, the function f, the blue line is the secant, and then you connect it to another point, and you just keep going until you eventually find the zero. And so it can be modeled by the following equation given here. And so basically, if we just code this iteratively in Python, we'll be able to solve this, right? So in order to do this, right? In order to do this, let's define a function, just any function. So I'm going to say, oh, let's not make it t. I was just used to the other parameters. Let's say x minus 5 times x minus 4 times x plus 4. Okay, right? So that's our function, right? And then so if we define secant, right, for the secant method, so if you look at this, you need two guesses. You need two guesses because you need to guess the first 2 points to which to draw your line, right? So we're going to say x naught is guess 1, x1 is guess 2, and then the maximum number of iterations, so let's just say it's 50, right? Eventually, if it's not going to converge, it's not going to converge, right? And then we're going to say our tolerance. So basically, we're going to be checking our values from this method, and then we're going to see if they're close enough for us to accept. And we're going to say our tolerance is 1 times 10 to the negative 10th, right? And then so to do this, we want to iterate. So we're going to say for I in range of the max iterations, right? And then we're going to start basically coding out this method. So first off, we need to evaluate the function at x naught and x1, right? Two guesses. So we're going to say f naught equals f of x naught, and then f1 equals f of x1, right? So get that out of the way. And then so x2, or in this case, x sub n, equals x sub n minus 1, so x1, right? Minus f of x1, so oh, minus f of x1, or f1, right? That's the whole point. Times x1 minus x naught over f of x1 minus f of x naught. So times x1 minus x naught divided by f1 minus f naught, right? So we've calculated the actual method. There we go. And then to know if this converges, right, what we're going to want to do is see if the difference between x2 and x1, so our second guess and our actual zero, is less than our tolerance. So we're going to say if the absolute value of x2 minus x1 is less than our tolerance, then what are we going to do? Um, we want to break out of the loop, right? Because that means we're done iterating. Um, and then maybe let's return a message if the function is successful. So we're going to say root equals root successfully found. We're going to say message, actually. And then if this doesn't meet the tolerance, right? So else, what are we going to do? We're going to update our guesses with our new values, so that's iteratively, right? So in this case, our x naught equals x1, our x2, our x1 equals our x2, and then we draw our line again, right? And then so we update the guesses. X1 x naught equals x1, x1 equals x2, and then we run the loop again. Um, and we want to, so what I want to return, oh, and I also want to say if on the last iteration we can't find it, root equals root could not be found. And then I want to return, or I want to message, not root, message equals, I want to return, what do I want to return? I want to return x2, because that's the root. Um, and then I also want to return how many iterations it took, and then I want to return the message, right? So let's try this. Let's just guess 0 and then 5, right? I don't even know what guesses we are. Oh, we shouldn't guess 5 because that's the actual one. The actual one. Let's 3.1415926535, right? Um, and then let's run this little bad boy. Look at that. So it took the root of 4, took 7 iterations, and the root was successfully found, right? Now we're gonna basically do the same thing here, but using Newton's method, right? And honestly, we can just compare, right? We can just compare um, a secant method with Newton's method. So what's Newton's method, right? It's given by this approximation, right? So basically, we're going to say the value of a root or a function is your initial guess minus the value of the function at that point divided by the value of this derivative at the point, because it's the line tangent to the curve, right? So this is like a graphical demonstration of Newton's method. But so advantage of this is A, it's way more accurate and it comes a lot faster, and B, you only need one guess, right? So if I'm to copy this, and then I'm going to make it Newton, but I only need one guess. So I'm going to say my guess is x naught, right? And so I need to compute the derivative, which is why I imported Jax all the way up there. So I'm going to say df equals Jax dot gradient, so the gradient, right, up x, just Jax dot gradient, okay, of f. Sorry, and so there should be an f here. Um, just making sure. Okay, I forgot one main argument. We need the function. Yeah. So Jax df equals Jax dot gradient f. Yeah. And then we're going to basically do this exact same loop. So for I in range max iter, and then so what values do we need? We need so let me go to Newton's method. We need f of x naught and f prime of x naught, right? So we're going to say f naught equals f of x naught, df naught equals df of x naught, right? And then the 0, x1, equals x naught minus f naught over df naught. And then I'm going to say f1 is just f of x1, right? And basically f1 should be 0, right? Because x is the 0 value. Um, and then, so our condition for our tolerance is just going to be if the absolute value of f1 is less than our tolerance, which is really, really close to 0. Then I want to do the same thing. I want to say the message is the root successfully found. come on, work with me here. And then I want to break, and then if not, I want to update it. So x naught equals x1, and then f naught equals f1, right? So we're gonna update to keep going, and then I want to return it the same way I did last time. So I'm gonna return what do I want to return here? X1, I, and then the message. Oh, and I also want the message. So remember, the secant method took 7 iterations to find it. So I'm going to do the exact same conditions I put in, but I'm going to do Newton this time. Oh, but I only need one guess. So I guess we can't really compare it. Let me guess 3.14159 like this. Secant, missing one required positional argument. It's there. I'm confused. Why did me? Oh, it's because I didn't put in the function. So I'm going to say f. Yeah, because I changed the f. The name Jax. Okay, it's because I didn't run this bad boy up here. Then let me run you. And then I'm going to run you. And you're going to work. Right, and so you get 4. And then it took 4 iterations, and the root is successfully found. So there you go. There's our method, our Newton's method, and our secant method for just 1D functions. Thanks.